All right, so this is the fourth session for the class. And to tell you the truth, I'm not really 100% sure what we covered last session. I know we're on chapters 5 and chapter 6 for this one, if we stay along. So at this moment, if you're on here live or if you're listening to the recording, for this series of classes, and we're running 3 classes simultaneously here. One group is going to be meeting at Eastern West Virginia Community College. Another's going to be meeting with Rural Action in Athens, Ohio. And another group's going to be meeting here in Marietta, Ohio, and their different dates and the like. But we're just running these Zoom sessions concurrently. So we're on the same track here. Chapter 5 is a recap of um, all of the parts of a PV system. And I should probably explain too, we're in a transition. I think we're operating, and again, I'm losing track, but we should be operating off of chapters off of edition 8 or edition 9. This is the edition 9 of the textbook. The main difference between the two, we upgraded a lot of the illustrations, but we also changed some of the format. So, as this book has developed over the years, chapter 7 got to be bigger and bigger and bigger and bigger until it felt like it was too much in one chapter. So, we kind of broke it into 3 chapters. So, if you're a little bit lost with my references to chapters, um, that's the reason for it. If you're operating out of the 8th edition, chapter 5 is parts of the PV system. Chapter 6 is the site assessment. If you're operating off of the 9th edition, let's see, chapter 5 is still parts of the system, and then the site assessment. So we're still good there. Then when we get into chapter 7, that's where some of it starts to split apart. Chapter 7 was basically overall design of your system, but we split that into design and installation of the array and the inverter, then wiring of the system, then energy storage systems was broken out, and then the mounting system, and then we have a standalone system. So all of those had been incorporated into chapter 7 and maybe little bits of it incorporated in other chapters. So the structure of that's a little bit different. So next chapter, chapter 7, if we're operating off of both of these books, we're going to get a little confused. But and the online program is still synced up with the 8th edition. So that's one reason we're sort of sticking with that as far as making our references. So any questions from chapter 5, the parts of the system? I think, give you a second to respond. I
I
think I went,
remember I
yeah,
remember we were looking at a lot of stuff last week about the wire gauges and the resistance is what I remember.
yeah. Okay. So the resistance, I think um, we're trying to do Ohm's law and voltage drop equation. Voltage drop equals amps times resistance times twice the distance divided by 1,000. The wire gauge, making reference to the table in the book. Um, I think we talked a little bit about the flow of electricity through the system, whether it's a standalone or a grid tied. That may have been a couple of weeks ago, but I want to kind of repeat that because it's very important. And now that you're getting into the parts of the system, you should be able to follow it maybe a little bit better. But if we look at this whiteboard, hopefully you're seeing the whiteboard, and when we look at the parts of a system, um, let's just look at a simple grid tied system. So the first part of a system is going to be the solar array. And then from the solar array, you go into either a combiner box or a junction box. So the combiner box or the junction box typically on a rooftop system is going to sit underneath the array. It's going to be mounted either to the rack or to the roof. And then the wires from the array itself, and the wires on the array itself are the only ones that are loose. Every other wire that you're going to be dealing with is in conduit or raceways or something like that. But really, from a practical perspective, it's tough to have wires in a conduit coming from a solar panel because they've got two wires coming off. They've got to be managed somehow and then moved into an enclosure. The enclosure that they move into is either a combiner box or a junction box. And the only difference between the two is in a combiner box, you connect everything in parallel. And in a junction box, you just use it as a transition point to move from one form of wire to another form of wire. In this case, the PV wire that's connected to the panels, it's very bulky and expensive. It's designed to deal with high heat environment, ultraviolet environments, things like that. So it's expensive, but you don't need it once you're running in conduit into the home. So now you're going to transition to a less costly wire, and that's done in a junction box. So we go from that combiner box or junction box. From there, we're going to go to a DC disconnect. And you can have more than one DC disconnect. In your book, some of the diagrams will have two disconnects. That's perfectly acceptable, especially for a ground-mounted system. If you've got a ground-mounted system, you probably want to have a disconnect out there at the array, and then another one at the house or wherever your equipment is going to be kept so that you can turn it off at either location. Think of it like shut-off valves in your plumbing system. So you might have a main shutoff valve for your house, but you also have shutoff valves under every sink. You have them at the toilet, wherever, the shower. All of these things have shutoff valves, and so having multiple ones really impact the issue there. So that's the case. So typically, the DC disconnect has to be located within 10 feet of your inverter, and externally operable. So oftentimes now, the majority of the time, it's going to be built into your inverter. So you've got your DC disconnect and it's connected to your inverter. So you come into your inverter, and then from your inverter, you're going to go to your AC disconnect. And the AC disconnect, then in a very small system, residential, you're typically going to go into a service panel. You're going to go into this breaker, and then you've got your main breaker. And from the main, it goes out to the meter. And then from the meter, you go up to the transformer, normally again on the pole, on the telephone pole. So this would be a very simple grid-tied system, all the different components, what they do. This AC disconnect is supposed to be located within 10 feet of the meter, and it's supposed to be externally operable. So you don't have to open it up with a screwdriver or something like that to get to the disconnect. It should be marked, and it should be lockable. That's another thing. You don't have to put a lock on it, but it has to be lockable and within 10 feet. And the reason for that is when the first responders come and they pull the meter, if there's a fire at the house, there'll be a label on that meter saying, hey, there's another source of energy here at this location. They're going to look around, and within 10 feet, they're going to see the AC disconnect, and it's labeled, this is the main disconnect for the PV array. So that's the whole reason why it has to be located where it is, because typically first responders and clearly the utility knows where your meter is. So that's where they're going to go. That's where they're going to go to make sure there's no power in the house. All right, so as electricity flows through this system, we can see that all of the power that's generated by the array flows through the wires, goes into your inverter, it's converted into AC, it goes to your loads, and then the first thing it's going to do is go to any load that's turned on. When you turn on a light, you turn on a dishwasher, whatever, electricity always flows the path of least resistance. It's going to the place, the most localized load. So the power from your array is the most localized source of power, and it's going to go to your load. And then if you have extra capacity, if you're generating more power than you need, the grid now becomes a load, and the power is going to flow out onto the grid. So all that that's doing is flowing. Think of it like filling a lower place. When water flows into an area, it goes to the lowest place first until that place is filled up level with the water, and then it goes to the next lowest, and eventually the whole load sort of spreads out. So the water reaches its level. Well, one interesting factor in all of this is, if you think about it, in order for the grid to be a load, then your system has to generate power slightly at a slightly higher voltage than the load, right? Than the grid. The power always goes from higher voltage to lower voltage. So it always flows in that direction. Just think like water goes from higher elevation to lower elevation. So if I want the grid to act like a load, then my system has to be generating power slightly higher voltage than the grid. But we want our power to match the grid. So there's a bit of a dance going on there. That's where your electronics come into play. But it's always going to be just a fraction higher voltage. Well, the impact of that is, if you start adding lots of power to the grid, then the grid's voltage is going to increase, right? Because all of this voltage that you're dumping onto the grid slowly elevates the voltage of the grid itself. So if you've got 100,000 homes and they're all pumping power out onto the grid's voltage is going to elevate. Well, how do you compensate for that if you're a grid operator? Well, you should think about the voltage sort of like water pressure. I keep using the water analogy, but it's pretty good. So the grid has to operate within a range, plus or minus 5%, plus or minus 6%, in that range. So this is how they kind of control loads as loads are turned on or turned off. Because if I turn on a light in my house, it slightly reduces the voltage of the entire grid. Obviously, tiny fraction, but it lowers the voltage. And when I turn off that light, the voltage is raised slightly until supply and demand compensate. So as I add more demand, the water pressure or the voltage goes down. As I reduce demand or I increase supply, the water pressure increases or the voltage increases, and we have a range of plus or minus 3% or 5% or 6%. Okay? That's how they modulate in the short term. So if they start to see a spike in demand, which is going to lower the voltage, grid operators turn on more turbines. They pump more juice into the system. They respond, and they have to respond quickly, because if that voltage drops below 6% under the median, the grid's going to crash. Power goes out. That's one of the reasons why you may read occasionally, if there's a transformer that blows or something like that in the system. We had a blackout that wiped out the East Coast back in like 2004. They blamed it on a single transformer up in northern Ohio, right? One transformer on the grid got touched by a tree branch and shorted out and blew out. Well, what does that do? As soon as you lose some of the supply, so that's what would happen when a transformer blows out, some of the supply is lost, which means voltage is going to fall on the grid because the loads didn't change, but the supply changed. And then it's going to drop, and then that's going to cause nearby transformers to kick off because you're falling outside of the operating range of the system. And so that one kicks off, which it makes the problem worse. And then you get these cascading transformers blowing. So then you end up with the grid shutting off. And most people think the grid can turn right back on again, but that's just simply not the case. Oftentimes, these power plants, when they shut down, there's what they call a black start procedure, and it can take a significant amount of time to get each of these things back online. And if there's damaged equipment, you got to replace that. So in this case, in 2004, that process ended up with like 3 days of power outage that covered almost the entire East Coast. So that's a big deal. Now, one of the things that solar was doing is we start to see, as more and more people adopt solar, and this was happening in California. California was the first place to adopt solar in a big way. So let's say you got 100,000 homes all connected to the grid and they've all got solar. Well, in the olden days, when the utility controlled all of the power and all of the generating, they monitored the loads and they controlled all of the generating supply. Well, now you're getting into a distributed generation system where they don't control all of the supply because individual homes are generating power. They also don't know what loads are connected to the grid, because if my solar array is generating power and my loads are being serviced by that power, AEP doesn't know how much I'm generating and how much I'm using. All they know is what's flowing through the meter. That's all they know. So there's a significant amount of power that's hidden from them. Well, this comes into play. Let's say that there's an instant power outage, just a flicker, where things turn off for whatever reason. We get those all the time, right? Just a transient thing, and it goes off, and you got to reset all your alarm clocks, and it's annoying, but that's kind of all it is. Okay, so all the power goes off for a second. Well, the old inverters were all designed that when they're turned off, when they're turned back on again, they go through a 5-minute handshake to make sure that they're syncing up with the grid signal. So it's almost like your modem's doing that boop, bump, all of that, where they're doing this handshake thing. But it was timed for 5 minutes, and all of the inverter manufacturers did exactly the same thing, 5 minutes to the second. Okay, so that's interesting. So then the grid goes off, boom, comes back on. Well, one big problem is they don't know how much power was being used. Before they did, but now all of these systems that had solar are going to want all of their power from the grid, not just the power they want, less what they're supplying, because their inverters aren't working, right? For that first 5 minutes, those inverters don't work. So the grid might get hit with a lot more demand than they were anticipating. If they do, the voltage is going to drop and the grid's going to crash again, right? So you get this one little flicker. All right, so they learned their lesson. They said, okay, well, we now know how much demand is out there. It's more than what we're supplying. So let's ramp up the demand. Let's kick the grid back on. However long it goes off, I don't know. So they kick it up, and let's assume they get the grid operating again. 5 minutes later, every single inverter that was built that's attached to the grid kicks on, and all of a sudden the demand on the grid just plummets, because now all my solar arrays are servicing my load, not the grid. So the load from the grid drops dramatically all at the same second, which causes the grid to crash again. So the grid is crashing. They're getting these cascading crashes just because they cannot predict what's happening with that, and everything's happening all at the same time with these inverters. So in order to deal with that, I forget which code cycle it was, but they began to require that you have a smart inverter. And that's where you get into the 1741 SA, right? Because the certification for inverters is 1741, UL 1741. Now they say SA, which is smart addendum, supplemental addendum, whatever, but it's for smart inverters. And those smart inverters are supposed to be smart enough to say, okay, when I turn back on, I'm not just going to wait 5 minutes and then turn back on. I'm going to look at the grid, And if the grid cannot handle me turning back on, I'm not going to turn on until it's ready, until the grid can handle it. So these things have basically a little bit more flexibility, a little more internal intelligence. They also can ride out those momentary flickers. You know, they will operate under less restrictive voltage requirements. So if the grid drops a little bit, you see sometimes your lights dim and then come back up. You know, that's just kind of a temporary, a transient voltage drop out there on the grid. Your inverter's designed to ride through that. So there's a lot of those kind of transient ride through things. And they'll also clean up the power, and they're doing all of this other stuff. So the utilities basically said, we want you to pay for that upgrade, right? You're causing us problems. We want these things to pay for the upgrades. You really can't buy an inverter today that's not a smart inverter. But there may be inverters out there on the market, is stuck in warehouses or whatever, that you can buy, older ones that are not smart inverters. So be sure you check with your utility, because your utility in the interconnection agreement is going to stipulate whether it's got to be UL 1741 or UL 1741 SA, or now they've got an SB. So make sure that whatever inverter you're using, you can use. Now, if you've got an older inverter, you don't have to trade it out. Those things are all grandfathered. But new inverters, make sure they're there. All right, so that's kind of a long sidebar there. So what I was getting to is, okay, so 100% of your array is generating power. It flows through your inverter, converts to AC. Some of it goes to the load, some of it's going to the grid. Let's say that it's not a good production day, and my array is not producing everything I need for my loads. Well, then we supplement what's going from the array, and it's going to the load from the grid. So you're pulling power from the grid, or you're sending power back to the grid. The main takeaway from this diagram, though, is 100% of whatever is being produced by the array is going through the inverter, right? It's going through the inverter, and it's either going to the load, or it's going to the grid, or a combination of both. Okay, but 100% of what you produce. So in this case, in a grid-tied system, the grid is basically a load dump. Okay, is anyone confused by that at all? All right, so then I'm going to clear the page here, and now I'm going to talk about a standalone system, because a standalone system behaves differently. So there is no grid, right? So you still have your solar array, and you're going to then go into a combiner box or a junction box. And then from the junction box, we're going to go not to your DC disconnect. There could be a DC disconnect. Let's draw one in here just in case. And then we're going to go to your charge controller. Okay, from the charge controller, we go to the battery. Well, by its very definition, a charge controller controls the charge from the array to the battery. It's like a traffic cop, right? If it needs power, I'm going to let it through. If it doesn't need power, I'm going to just shut off. I'm not going to overcharge my battery. I'm going to monitor it. I'm going to charge it in a way. In chapter 5, I think we talk a bit about the charging cycles of lead acid batteries, where there's bulk charging, then there's absorption, and then you get into float. And the reason for this is it's a little bit more efficient than the older form of charging. Think about the old form. When we talk about a series charge controller, we think of it like a thermostat, right? When the battery drops to a certain level, you allow it to charge. Once it gets full, you turn off the charge until it drops to a certain level. Then it kicks on. So it's either on or it's off. And there's a large time there where your solar array is capable of producing, but it's not, because it's just waiting for the batteries to drop down to a certain level. So this mode, bulk absorption float, is a more efficient form of charging. And I just noticed in the chat, Zach had asked, what does the inverter do when you lose a leg from the grid? All right, so I'm assuming you're saying, okay, we've got single phase electricity. It could be three phase, I guess. And you've lost one of line 1 or line 2. So now you're hooking up to 120. It's going to shut off. I mean, it needs to see 240 volts. If it's not seeing a grid as it's supposed to see it, it's just going to shut off. If you've got battery backup and all of that, you're probably going to go into standalone mode. So, although I think losing a leg of the grid is fairly unusual, that would have to be a very localized disruption, I would imagine. So, I don't know. Maybe I'm wrong. I'm not familiar with. It's never happened to me. So, all right. So let's say, okay. So we're doing the charge controller now. Where do we go from the battery? We're going to go to our inverter, and there might be a DC disconnect, built into that inverter. Why not? Maybe. And then we go to our inverter where the power is changed from DC to AC. From the inverter, we don't have to go to an AC disconnect that's out by the meter because we don't have a meter, right? So I'm going to go and let's just say that now this is my main. And then this goes to the loads. And what's typical in a standalone system is here in the inverter, you might have a generator hooked up. So in those days where you're not getting the kind of power that you need, you've got a backup generator. So you don't have to size your system huge. All right, so how does this flow of electricity work? Let me get rid of some of this writing down here. All right. Okay, so what determines, well, the power from the array flows through here and it goes to the battery. Now, if there's no load dump, what happens when the battery is full? Well, the charge controller just turns it off, right? The array is sitting there. It's capable of charging your batteries, but it's not because there's no load to man it, to fill. Okay. Now that's one of the reasons we often will put in a load dump, like a hot water heater or something here, and it's controlled by the charge controller, because when the battery is full, the charge controller may then take all that extra power and redirect it into the hot water heater. That way you're just not wasting the power. It's not a bad thing. The array can sit there all day long, not doing anything. It doesn't damage anything, but it's a waste. It's an opportunity cost. That's basically what you're dealing with. So now we filled up our battery. Now think of this as two separate systems, with the battery being the demarcation point here. So what happens when I turn on a load? Well, the inverter pulls the power from the battery and it goes to the load. All right. So all of the power. So if I turn on more loads, it pulls more power. And it only pulls what it needs, right? There's no grid to send this to, no load dump there. So it's going to pull that power through. So how do I size the inverter? The inverter size is based on the maximum loads I might run at any one time, which is called the maximum power draw. So when I go to size my inverter, I take my maximum power draw, and because you don't want to run your car at full speed all the time, you need to give it a little bit of capacity, excess capacity. We usually take the maximum power draw and we try and multiply it by about 1.25. Give yourself a little bit of an overage. So if I add up all of my loads that could be operating at the same time, and I find that I've got 2,000 watts instantaneous power. Remember, power is in watts and energy is in watt hours. Energy is power over time. Okay, so if I can, when I turn on all the different loads, it adds up to 2,000 watts of instantaneous power requirement. I'd probably go out and pick a 2,500 watt inverter. Okay, if none of these loads were motors, that would be for sure. Now, if I pick a 2,500 watt inverter, you'll probably see on there that it says 2,500 watts continuous and 5,000 watt surge. And the reason for that is because some of your loads are going to be motors, right? You're going to have a refrigerator, you're going to have a pump, you're going to have all this other stuff. Well, when a motor kicks on, for a brief second or two, it has a surge. It has a surge on demand. So you probably noticed it in your homes at some point when a big load turns on. Maybe it's in our house, it's the well pump, the cistern pump. When it kicks on, sometimes the lights will dim just slightly, and then a second later, everything's returned back to normal. That's because that load for that second drew a huge amount of power, which then caused the voltage within your home to fall a little bit until that surge evened itself out. So your refrigerator, when it first kicks on, maybe it draws 1,200 watts. And then, after a second, it's only drawing 350. So you've got to account for that surge. So these guys, the inverters here will say it's a 2,500 watt continuous with a 5,000 or a 4,000 surge. And usually in a household, having double for the surge is plenty. But if you're setting up a system where you're only operating heavy equipment, like let's say you're doing it in a barn where you're running milking machines or something like that, you might want to put in a much bigger inverter just because that surge capacity might need to be bigger. Or if you go out and if you're doing a small system like a solar generator or something, and you bought your inverter at Harbor Freight, know that that thing's a piece of crap and it's not going to meet whatever its surge protection says it is. It's just not going to do it. So buy yourself a bigger inverter. It's like Jaws, right? We're going to need a bigger boat. So you're going to need a bigger boat for this. There's never a problem putting a bigger inverter in. So let's say I have 2,000 watts. I think I need a 2,500, but I decide to go out and buy a 4,000 watt inverter. No problem. You've got more capacity than you need. You may have spent extra money that you didn't need to spend, but that, and you never know because maybe that 4,000 watt inverter was on sale and it was cheaper than a 2,500 watt. So you run into those all the time. So don't feel like it's a problem if you put too big of an inverter in there. Contrarily, if you've got a generator built into this system, it's generally going to be generating AC power. And it hooks into your inverter. And that inverter, if it can accept a generator, is usually called an inverter charger. And the reason for that is because all that generator is doing typically in these systems is recharging the batteries. So it's generating power to your inverter, and then the inverter is recharging the battery, and the battery is servicing the load. Okay, so that's what the generator is doing, and that's what's being controlled within the inverter. So you're not running the generator that goes directly to your loads. That's not happening in most of these cases. It's simply recharging your batteries. And these things can have automatic settings where if your battery drops below, say 20% or 30% or 40%, whatever you set it to, the generator will kick on and it will recharge the battery until it gets to whatever set point you've set that for. And those are there for the backup on cloudy days and extended storms and stuff like that. Just an added thing. So what I'm trying to point out here, though, is you size your inverter based on the maximum power draw in a standalone system. In a grid tied system, remember I said everything from the inverter goes, everything from the array goes through the inverter, and it either goes to the loads or it goes to the grid. But 100% of whatever is being generated by the array goes through the inverter. The inverter doesn't care what your loads are. If your load is zero, it's still processing 100% of the power from the array. It's just sending it all to the grid. And if you need power from the grid to meet your loads, well, the inverter doesn't care. It's not part of that transaction, right? So all it's doing is pulling power from the array and sending it either to the load or to the grid. So in a grid tied system, you size your inverter based on your array. In a standalone system, you size your inverter based on your maximum power draw. Completely different approaches and completely different product. You cannot use a grid tied system in a standalone, and you cannot use a standalone inverter in a grid tied system. These things simply will not work. You don't want you just so make sure you got the right inverter. And a bimodal inverter does both, right? It will work in a standalone mode. It will also work in a grid tied system. So it's a more expensive, more complicated piece of equipment. That gets the best of both worlds. The downside of having a grid tied system is that when the grid goes down, your system is off, and that's something that can be annoying, because when you're, a lot of people, especially if you get into this as a business, your customers say, I want a solar array. Why do you want a solar array? Well, I just want a solar array. Well, then it turns out really what they wanted was backup when the grid goes down because the grid is unreliable. But they also are cheap. So they're saying, okay, I just want a grid tied system. And you say, okay, but when the grid goes down, you'll have no power because of anti-islanding. We're not allowed to pump power back out onto the grid when the grid is down because it could kill a lineman when they're out there working. There's power being generated and they don't expect it. So, but then after you've installed the whole thing and the first time the power goes off, the customer calls you up and says, what's the deal here? My system doesn't work. And you say, well, is the grid down? He goes, yeah. He goes, well, it doesn't work when the grid is down. He goes, well, that was the whole point I put this thing in. I wanted power when the grid goes down, and then you go, all right, we went through this 12 times but you're still the bad guy. So that's why you want to first off communicate well. But secondly, that's when the bimodal systems, the AC coupled, the DC coupled systems, those are nice because you get the best of both worlds. You're dealing with it as a standalone, as a grid tied system when the grid is available, and you're dealing as a standalone system when the grid goes down. And if you have a very unreliable grid, you should probably think about having an AC coupled or a DC coupled system. Okay. While I'm talking about AC coupled and DC coupled, well, first off, I should open it up. Does anybody have any questions here as I've been ranting through? Give you that option. All right. So
yeah. What about the sizing of the battery system here in that example? How do you size that for how much time you want to run off the battery?
Yeah. Okay. Well, let me pull up the whiteboard here. If I can find it. How do I do that? I know I had whiteboard. I've lost track. Oh, there it is. New whiteboard. There we go. Okay. Yeah. When we get into battery sizing, this is a little bit of a preview. Maybe people have gone along, but before I get the battery size, let me just tell you about the array size. How do you size an array? And typically the array is pretty straightforward. You just say, okay, what's my daily load? So your daily load for a typical home in America, it's right about 900 kilowatt hours per month. So we would divide that by 30 and a half days per month. And we get I'll pull out my calculator. It's going to be around 30. 29.5, right? 29.5. In this case, it's kilowatt hours per day. Now we need to know how many hours of insolation we have per day. And the tool that we use for that is PV Watts. So if I let me close the whiteboard here and let me jump in. If I share my screen, this is, yeah, share. Okay. What are we seeing here? Oh, this is my emails there. All right. So PV Watts. So we jump in. Are you guys seeing PV Watts on the screen? Okay. So you would just take your address, or you can put in a zip code. So if we say Athens, Ohio, which is 45701, and we can go in here, you can give it a specific address, and now it's going to say, all right, is that the right place? So they kind of allow you to zoom in here, but you can see that that's the right location. And now it's going to ask us what the system size is. For this exercise, we don't care what the size is. It will allow you to figure out your D-rate losses. And this calculator here gives you all of the different things that could add to the D-rate of your system. They're saying soiling is going to be 2%. That might be a little extreme. Soiling is just dust and pollen and things like that. Normally, rain's going to take care of it. So let's put that to 1. Let's assume we have no shading issues. This is out there in a place, they're putting 3% in, but I'm going to change that to 0. Snow loading, I'm not going to do. Mismatch of panels. So the D-rate on mismatch of panels is if you have 2 panels and one produces 2% more than another one does, there's usually plus or minus 2% or so. One was made on a Monday, one was made on a Wednesday, they're the same panel. As long as you're hooking them together as a string, whatever the worst one is what you're getting. So if it's a plus or minus 2%, it's really minus 2%. If you're using module level power electronics like a power optimizer or a microinverter, you can drop that down to 0 because every panel operates at its own level. So plus or minus 2% is basically going to even itself out. So let's assume we're using optimizers or power electronic module inverters, microinverters. So I'm going to put that at 0. Then wiring, that's voltage drop. So it's saying 2% voltage drop. Remember, we wanted it 2%, no more than 5%. There's going to be some loss due to connections. All of the different hardware, every time you make a connection has a little bit of loss. 0.5%'s not bad. Then they have light-induced degradation, LID. And this is one of those things that's kind of weird, but basically it's like getting rid of your new car smell. As soon as you put that thing out there in the light, it has a loss within the first week or two. And so there's kind of nothing you can do about it except buy special panels. Nameplate rating, that again is if it could be better, could be worse. I would say in today's market that should be at a 0 because they're basically saying it's going to produce what we tell you it's going to produce, and it might produce more, but it's not going to produce less. And then the one that they always throw in is availability. They're saying, okay, 3% of the time your system's not going to be working. You're going to be working on it. You're going to be repairing it. Something's going on. That's pretty steep for a residential system. Let's just put that at 0. So at this point, now we're down to about a 5% loss rather than 14% loss. I don't know where they get the 4 point. So let's just say it's 5%. So we put that in here. And then you've got tilt. That's the angle of the roof, right? So on a typical roof, let's say it's 20 degrees. And then your azimuth Your azimuth is based on, what direction the array is facing. And you're going to have to figure that out with your site. And there are tools that'll help you do that. 180 degrees is south. That's solar south. 0 is solar north. 90 is east. 270 is west. So let's just say that we're almost at south. How about 170 degrees? Not quite south. And you'll measure that on your roof. So I've set the thing, it's 20 degree tilt. And now it's saying for this location with those parameters, we're going to get 4.43 hours of insolation per day. Okay, so that varies. It varies on your location. It varies on your orientation. It varies on your D rate. But with all of the specifications we plugged into this tool, Athens, Ohio, almost south, 20 degree angle with that D rate, we're going to get 4.43 hours of insolation. Well, that comes into effect. I'll jump back into my whiteboard. And so what did we say? 4.43? So 4.43 hours per day. Well, if you divide kilowatt hours per day and hours per day, now it's 29.5. 29.5 divided by 4.43, and we get 6.65. So 6.65, and it's going to be kilowatts. So for this site, with this load demand and this amount of hours of insolation, we need a 6.65 kW system if it's 100% efficient. But we just figured out it's not 100% efficient. We figured out it's only 95% efficient, right? Because we did our D rate. So 6.65 divided by 0.95 is going to get us exactly like 7 kW. So that's how you size that array. That we need for this house a 7 kW system. So that's how we get to sizing our array. It's a 3-step process. Get your daily rate or your daily load demand, divide it by the hours of insolation, and then divide it by your efficiency. If you end up multiplying it by the efficiency and getting a smaller number, you know you did it backwards. Because if you think about it, I need this if it's 100% efficient. It's not, so I'm going to need a bigger system because it's not 100% efficient. If I end up with an answer that's smaller, I know I did the math backwards, because obviously if something's not 100% efficient, you should need more of it, not less. Okay, so I'm going to get rid of this and then I'm going to answer your question there, Morgan, which is how do we size a battery? So the battery system, we start again with our daily load. So in that case, it was 29.5 kilowatt hours per day. So let's assume we're talking about the same place. And now we want to get from kilowatt hours per day to amp hours. So because of the power equation, watts equals amps times volts, what do I do to get from kilowatt hours to amp hours? Well, in this case, I divide by volts. So if it's a 48 volt system, which most of these are going to be, I've got a 48 volt. Well, then I need 29,500, which is 29.5 kW. So 29,500 watts divided by 48 volts gives me about 615 amp hours. All right, so this is going to be a huge battery bank, by the way, because you don't normally do battery backup for a whole suburban home like this. But let's say we're going to, because you're just interested in seeing how much this costs. All right, so it would be 615 amp hours, 48 volt system, if we could use the whole battery and if the system were 100% efficient. but we can't. So now with a lead acid battery system, we have to decide, what is our depth of discharge? How much of the battery can I use? Normally with lead acid batteries on a standalone system, you want to stay right at about 50%. Okay, so in this case, we're 50%. Let's see, it says on PV watts, solar radiation was 4.43. Is that the equivalent of 4.43 hours of insolation per day? Yeah. Because what basically, the question was, it says 4.43 kilowatt hours per square meter per day. And that's insulation is 1,000 watts per square meter, or radiance is 1,000 watts per square meter. And we're just, what we're doing is just taking the radiance, which is measured in watts per square meter. We're turning it into hours, which is insulation, for the reason because we need it in hours to do the equation. So I'm going off onto the tangent of that question. But all right, so let's say that we do a 50% depth of discharge. So we can only use half of it. Well, that's really going to be the equivalent of doubling. So it's going to be 1,230. So now it's 1,230 amp hours because I can only use half. And now I need to know what is the efficiency of the system. So the only piece of equipment, if I look at my system, and here's my array, here's the combiner box, here's my charge controller, here's my batteries. From the battery, I go to my inverter, and from the inverter, I go to my load. What is the only piece of equipment between the battery and the load? Well, it's the inverter, right? It's the only thing that's going to inject loss into my system from the battery to the load. So I'm not derating this based on the efficiency of the overall system. I'm only derating it based on the efficiency of the inverter. So if I look up the spec sheet on that inverter and find out it's 97% efficient, I can do that here, and I'll do 12 divided by 0.97, and now it's going to be 1268 amp hours. Okay, and now I'm trying to rack my brains here. I haven't done this in a while. There's one other thing we have to worry about in here. Depth of discharge, efficiency. Does anybody know? It's a minor thing. All right.
How many volts the battery is?
No, we did that at the very beginning when we did the 48 volt. I should have it's frustrating, and my old age catching up to me. Let me see if I think I've got the equations in the back here. Formulas.
So this is turning into a huge battery here.
Yeah, it is for sure.
Yeah.
Depth of discharge. Nope, that's it. Load demand, system voltage, depth of discharge, efficiency. I just thought there was one more thing. All right, so 1,268. And remember, it's a 48 volt system. So let's say, okay, 1,200. So if I drop out of there, and now let's just sort of look at, let's jump in here, and let's go to let's look at a 1,500 deep cycle. 1,500. That's a 200 amp hour. That's a lithium deep cycle 200. You can see that when we get into Let me look at forklift batteries. Let's just see what this battery is. 24 volt. Pull that up. Notice it's $4,000. So tell me it's 24 volt, 875 amp hour. So we're going to need two of those, two strings of those, right? But it's 24 volts. So we're actually going to need four of those batteries to meet our load demand. Four of those, $16,000 worth of batteries there. That's about what I would have expected. And each one weighs 1,750 pounds. So now we're talking about almost 3.5 tons of batteries for this house. So this is one of those reasons why lead acid batteries were just simply not practical for homes, as a battery backup. But in the meantime, now, if we think about how we size lithium ion batteries, let's see, residential. The world gets a lot easier. If I go into shopping here, let's see, like Renogy. Yeah, we'll pick that. Why not? All right. Notice it's a 48 volt system. When it first comes up, if it comes up, here we are. It's on sale. It was $7,800, but this thing's $3,100 for a 10 kW system. Well, how much when we're sizing the lithium ion batteries, it really is a whole different world, where we do it based on daily load. So we already know we need 29.5 kilowatt hours per day. So what size battery would we need? Well, we'd need a 30 kW, or probably two 15 kW systems. So in this case, all of the D rate, all the depth of discharge, all of those calculations are figured in when you're doing this. So in this case, using lithium ion, I need two of these for that same situation. So in this case, it's only going to be, say $10,000. A lot cheaper than the lead acid. We're not going 3.5 tons, because by the time I get down here to my specs, each of these batteries is going to weigh 443 pounds. Still pretty heavy, right? 800 or 900 pounds. That's not something you want to hang up on your wall. That's one of the things that drives me nuts when you see the advertisements for this stuff, is they stick them up on a wall like it's easy to lift 300 or 400 pounds. Like, look at this here. Yeah. Oh, well, here, at least they've got it on the ground. And that's typically the way you want to do it. So this is one reason we're going into lead acid, is we're going into lithium ion. I said lead acid. Yeah, lead acid batteries were not practical for anything but very small systems. Lithium ion, they're cheaper now. They're more energy dense, which means you get more power for less weight, less volume, and it's just a better system. So this is one of the reasons now, the advent of lithium ion batteries. One reason 50% of all the installations now incorporate batteries, because it's economical to do so. All right. I see we're up to the time limit. Anybody have any quick questions before we jump out? I know we're sort of all over, but we're starting to get into the math, and that's where people get confused. The main math questions, and ideally next time we'll jump into some more of them, but we did how to size a solar panel or a solar array, how to size a battery bank. And next time we'll try and talk a little bit about string calculations. When we're using a string inverter, what's the maximum length of a string? What's the minimum length of a string? How do you determine that? So those are kind of the voltage drop, you throw that in, and that's the math that freaks everybody out. It's not super hard, but there's a lot to remember, a lot of steps in it. So, all right. Okay. Well, we'll see y'all next week. And
Okay.
in the meantime, take care.
Okay, you too. Looks good.
All right. Bye-bye.